it makes a lot of things more expensive. Certainly things that are bought with credit, but then it has downstream effects on even things that aren't bought with credit.
Elon Musk has surprised everyone again, because what Tesla has built isn't just a new engine. It's a warning to every car maker on Earth, a breakthrough that could end the race before it even begins. And when experts like Sandy Munro, who has spent decades tearing down and analyzing vehicles, opened it up, what he saw inside completely changed his reaction. Something inside this system didn't behave the way a normal engine should. The kind of detail that doesn't just surprise engineers, it's a leap the industry never believed was possible. Tesla hasn't just pulled ahead, it has almost erased the competition. But what exactly did experts discover inside Tesla's engine? And why is it considered one of the most powerful breakthroughs in modern automotive history? Let's dive in. Tech giants versus Tesla. Back when electric vehicles were starting to become a serious industry, almost nobody expected Tesla to be standing where it is today. In fact, many people expected the exact opposite. Tesla was a small startup trying to challenge companies that had been building cars for generations. Ford, General Motors, Toyota, and Volkswagen. By the mid-2000s, Volkswagen alone operated more than 100 factories. Together, these automotive giants were producing tens of millions of vehicles every year. Tesla, meanwhile, was fighting just to stay alive. In 2011, electric vehicles made up barely a fraction of global car sales. Many analysts believed EVs would remain a niche market for years. And if electric cars ever did become mainstream, the common belief was that the traditional giants would eventually take over. After all, they had the factories, the suppliers, the experience, and the money. Tesla had none of those advantages. Then the giants finally entered the race. Billions of dollars began pouring into electric vehicle programs. Volkswagen announced huge EV investments. General Motors promised an electric future. Industry experts started talking about the arrival of so-called Tesla killers. On paper, it made perfect sense. Tesla's lead should have disappeared. Instead, the gap got bigger. While rivals spent billions trying to catch up, Tesla kept moving further ahead. By 2023, the Tesla Model Y became the best-selling vehicle in the world. Not the best-selling electric vehicle. The best-selling vehicle, that outcome wasn't supposed to happen. Which raises a much bigger question. What exactly was Tesla doing that everyone else wasn't? Most people assume the answer was batteries. Others point to software, self-driving technology, or Elon Musk himself. But some engineers who studied Tesla's vehicles came away focused on something far less obvious: the drive unit. One of those engineers was Sandy Munro, a manufacturing expert who spent decades taking products apart. In fact, when Munro first examined an early Tesla Model 3, he heavily criticized its build quality. He thought Tesla looked inexperienced. Then his team dug deeper. They opened the electronics. They examined the engineering hidden underneath the body panels. And eventually, they reached the drive unit. Suddenly, Munro's tone changed. The company he once criticized seemed to be doing something very different inside its machines. Something that looked years ahead of what many competitors were building. But before we understand that breakthrough, we first have to understand the problem every electric vehicle company faced at the time. The invisible wall in EV. Electric vehicles look simple on the outside. But within the industry, there was a problem that almost nobody could escape. It was not batteries, it was physics. To make an electric motor produce more power, you need to push more electrical current through copper coils. That sounds easy, but inside the system it creates a chain reaction that gets out of control very fast. Because heat does not grow in a straight line. it explodes. According to physics, heat loss follows a simple rule. Power loss equals current squared multiplied by resistance. That heat does not just waste energy, it attacks the motor itself, damages components, and forces heavy cooling systems just to keep everything alive. At higher speeds, another problem appears. Electric current does not flow evenly anymore. It gets pushed toward the surface of the wire. Engineers call this the skin effect. That increases resistance, which means even more heat. Spinning magnetic fields also create unwanted currents inside the metal structure itself. These are called eddy currents. They act like a hidden brake inside the system, producing heat exactly where it is hardest to remove. So the industry was trapped. If you build for performance, the motor overheats and wastes energy. If you build for efficiency, you lose power at high speeds. Engineers treated it like a fixed wall in physics. You could choose one side or the other, but you could not cross it. And the cost of that wall was massive, because if you could reduce that heat problem even slightly, you would unlock lighter cooling systems, fewer parts, and more driving range without increasing battery size. Even a small gain of 5 to 8% efficiency could save manufacturers hundreds of millions at scale. So the industry was not lacking effort, until that same amateur company, Tesla, stopped treating the wall as a rule. It began building something that forced engineers to rethink the entire idea of how an electric motor is supposed to work. Inside the spinning core. Inside an electric motor, there is one part that decides almost everything. It is called the rotor. This is the spinning core in the center. The outer part of the motor creates magnetic forces, and the rotor is what reacts to those forces and turns motion into actual movement for the wheels. Simple idea, but the reality gets extreme very fast. At around 20,000 revolutions per minute, this becomes a serious limit. The forces inside the rotor become so intense that every tiny part inside is effectively under thousands of times its normal weight. The magnets try to escape outward. The steel structure begins to stretch. Even the bonding materials start to fail. In most electric motors, this is the breaking point. So the real challenge was not how to make it faster. It was how to stop it from failing. Tesla's answer was not to slow it down. They wrapped the rotor in a thin layer of carbon fiber. But this was not a simple cover. Tesla built a precision process where a continuous strand of carbon fiber is wound around the rotor under extreme tension. As it tightens, it creates constant inward pressure, compressing the rotor from the outside. So instead of the parts inside trying to fly apart, they are locked in place, even under extreme rotational speed. And here is where the shift happens. Because once the rotor is stabilized, Tesla can push RPM far higher than what most traditional designs can survive. And in electric motors, RPM changes everything. Power is not just force. It is force multiplied by speed. So by increasing rotational speed dramatically, Tesla could reduce size and weight while still increasing output. That is how they ended up with a motor small enough to carry by hand, yet powerful enough to produce over 1,000 horsepower. When engineer Sandy Munro and his team studied this design, their reaction was not about small improvements. It was realization. Because this was not something sourced from suppliers or built on existing automotive systems. Tesla had created both the motor and the way to manufacture it, from scratch. But here, you might have a question. If Tesla is doing this, why hasn't any other big company done it? The manufacturing nightmare. What Tesla did with the motor sounds impressive on paper, but the real problem started after the idea. Because building it once is not the hard part. Building it thousands of times, exactly the same way, is where most companies fail. This is where the so-called manufacturing nightmare begins. The key process is carbon fiber wrapping. In simple terms, a thin carbon fiber strand is tightly wound around the rotor. But this is not a normal factory step. In traditional industries, carbon fiber parts are usually made for aerospace or supercars, where each piece can take days, sometimes weeks, and is carefully built almost like a handcrafted object. Tesla had to turn that into a mass production process. And that is where everything becomes extremely sensitive. Because the winding tension has to be perfect. If it is even slightly too loose, the rotor expands under force. If the tension is too high, the carbon fibers themselves start developing hidden micro cracks. At first, everything still looks perfectly fine, but under repeated heating, cooling, and extreme stress, those cracks slowly grow in silence until the structure eventually fails. There is no safe middle zone that is simply good enough. The margin for error is unbelievably small. And at 20,000 plus revolutions per minute, even the tiniest flaw becomes dangerous. A tiny misalignment, something as small as a milligram, can create destructive vibrations strong enough to tear the entire motor apart from the inside. This is why the machines used to build it cannot be normal equipment. And that is exactly the part Tesla has already paid for, inside its own factories. For any other company trying to copy this, it is not just about understanding the idea. It is about reaching the level of precision needed to build millions of identical motors without failure. And that gap becomes almost impossible to close at scale. But the race doesn't stop. Because once production becomes stable, the next question is not just how good it is how cheap it can become. The $1,000 target. What Tesla made is not just a motor. It is the complete propulsion system of the car. The electric motor, the power electronics that control it, and the single-speed gearbox, all combined into one compact unit. And the target is simple, around $1,000 to manufacture. Most legacy automakers buy similar systems from Tier 1 suppliers. And because everything is split into separate parts, they often end up paying between $3,000 to $5,000 per unit. That gap does not sound dramatic at first, but it becomes massive at scale. If Tesla saves just $2,500 per car and produces 500,000 vehicles, that is over $1.2 billion in advantage in a single cycle of production. Immediate structural advantage. And that changes everything. Because now Tesla has something most companies do not. It can lower prices aggressively, push competitors out of the market, and still stay profitable. Meanwhile, other automakers are forced into a corner, match the price and lose money, or keep prices high and lose customers. But cost reduction is not only about competition, it is also about control. Most electric motors depend heavily on rare earth materials like neodymium and dysprosium. These are essential for strong permanent magnets, especially at high temperatures. A large part of global processing happens in just a few regions, which means geopolitical tensions can quickly affect both availability and prices across the entire industry. And you know how Tesla solved this problem? It redesigned its motors to reduce this dependence almost completely. The same approach is applied to silicon carbide, the expensive material used in power electronics. Instead of relying heavily on it, Tesla changed how electricity is controlled inside the system, reducing the need for it while still keeping performance and efficiency intact. Even the physical factory setup is different. The new drive unit takes up much less space to produce, roughly half the floor area compared to older systems. This means fewer machines are needed, and once a company figures out how to build a powerful, low-cost motor, you know what it does next. It scales. The scaling machine. In 2017 and 2018, Tesla went through what Elon Musk called production hell. The Model 3 ramp nearly broke the company. The factory lines were over-automated, and entire production steps kept collapsing under their own complexity. Because Tesla did not just design cars, it learned how to survive manufacturing at scale. And that learning now powers everything it builds. Today, Tesla's scaling machine runs through its gigafactories. Fremont was the starting point. An old GM and Toyota facility pushed far beyond its original limits. It was chaotic, but it became the testing ground for every mistake Tesla had to fix. Then came Shanghai. Built from empty land to full production in just 118 days, Berlin and Austin took it even further. These were not retrofits. They were designed from the ground up around massive casting systems and simplified vehicle structures that remove complexity before it even reaches the assembly line. But the real advantage is not just factories. It is control. Tesla does not just assemble cars. It controls much of the supply chain behind them. It builds its own battery cells and structural packs inside its own facilities. And it writes its own software instead of depending on external suppliers. This is why when global chip shortages hit the auto industry, most companies slowed down. Tesla adapted. Because it could redesign software to work with whatever chips were available, instead of waiting for perfect supply. And here is where scaling becomes something more dangerous. More production means more learning, where dozens of separate metal parts are replaced with a single structure. That reduces cost, which allows prices to drop, which increases demand. Meanwhile, competitors are struggling to stay alive in the same cycle. Ford loses billions on its EV division. Rivian burns cash on every vehicle. Lucid depends heavily on external funding just to continue operations. Only BYD comes close, using its own deep battery manufacturing routes to compete at scale. But even then, the gap is not simple. Because Tesla is no longer just scaling production. It is scaling an entire ecosystem, the unreachable ecosystem. When you zoom out far enough, Tesla stops looking like a car company and starts looking like something much harder to compete with. Because the real power is not in one product. It is in how everything connects together. Start with the cars on the road. Over 7 million Tesla vehicles are already driving across the world. And each one is not just a car. It is a moving data machine, collecting real driving information every second. Tesla learns from chaos, unmapped construction sites, sudden lane changes, extreme weather, rare edge cases that no simulation can fully recreate. Every unusual moment gets captured, stored, and reused as training data. Tesla uses a vision-only system. No radar, no extra sensors, just cameras. A neural network that does not follow fixed human rules like it learns directly from millions of real human driving patterns and slowly builds its own understanding of the road. Now connect that to Dojo, Tesla's custom supercomputer built specifically to process driving video. When one car finds a rare situation, it uploads a short clip. Then, that improvement is pushed back to every Tesla on the road through software updates. Even software is becoming the next layer. Tesla is already in discussions where competitors may license its self-driving system instead of building their own from scratch. And that is the turning point. Because at that stage, you are no longer competing with a car company. You are paying the company that defines how your car thinks. So in the end, we have Tesla with its unusual journey from a small outsider nobody took seriously to becoming one of the most powerful forces in the entire EV industry. A company that started by improving one engine and ended up building a system where every part strengthens the next. But before we end this video, we want to hear from you. Do you think Tesla has already pulled ahead of the entire market? Or are companies like Ford, GM, and others still in the race trying to close the gap? Let us know what you think in the comments below. If you like this video, make sure to give it a thumbs up. And if you do not want to miss more incredible stories like this, subscribe to the channel. We'll see you in the next one.